Hello, everyone. Welcome back to AllAboutRx. Today, we are talking about the most important part of physical pharmacy, physicochemical properties. These properties help us understand exactly how drugs behave in our body and how we can make them both safe and effective. It's like a giant puzzle, and today, we're going to put the pieces together.
So, here's our roadmap for this explainer. We'll start with a quick intro to these properties, then look at physical properties at play, tackle the polymorphism problem, dive into chemical properties and absorption, and finally wrap up with keeping drugs stable.
Let's get right into Section 1, Intro to Physicochemical Properties. Now, you might be wondering, what happens before a raw drug ever becomes a pill? Well, we do pre-formulation studies. Why? Because our very first mission is always to ensure that drug delivery is completely safe, that is, non-negotiable. If we don't understand the basic traits of a molecule, we just can't guarantee it won't harm the patient.
And of course, it must also be highly effective, which is honestly impossible if we ignore its measurable physical and chemical traits. I mean, a drug that is safe but does absolutely nothing to treat the disease is pretty useless, right? We have to achieve those therapeutic outcomes.
So, these physicochemical properties act as the variables to our puzzle. They dictate everything from a drug's ADME, that's absorption, distribution, metabolism, and excretion, to exactly what kind of packaging it requires. They determine how we design the formulations and how the drug crosses biological membranes. Basically, every single decision a formulator makes comes right back to these core factors.
Moving right along to Section 2, Physical Properties at Play. Let's start with the basic states of matter. Drugs can be solids, liquids, or gases. Most drugs exist as solids, the typical white powders and crystals. But nitroglycerin is actually a liquid at room temperature. This single physical trait dictates that we must put it in soft gelatin capsules so it can be contained properly and absorbed quickly by the body. You simply cannot press a room temperature liquid into a standard hard tablet.
Now take a look at the graph on your screen. Notice how smaller particles drastically increase surface area. When you make a particle smaller, its surface area shoots way up. This helps the drug dissolve faster and enter the body quickly, just like we see with micronized griselfulvine. You're taking one large particle, breaking it down, and suddenly the surface area exposed to the solvent skyrockets. More surface area means faster dissolution.
That brings us to Section 3, the polymorphism problem.
So polymorphism is this fascinating situation where the exact same drug molecule can exist in entirely different crystal shapes, and each shape has different solubility and stability. We constantly have to weigh the trade-offs here. Crystalline forms have a defined, tough structure, making them super stable but harder to dissolve. On the flip side, amorphous forms lack that structure, so they dissolve beautifully, but they are inherently less stable and prone to shifting back into a crystal state over time.
And the stakes here are incredibly high. Just look at ritonavir. An unexpected, less soluble polymorph suddenly appeared in the tablets, leading to a massive product recall. Formulators thought they had a stable, soluble product, but the drug actually shifted its crystal structure right during manufacturing. That new polymorph wouldn't dissolve properly in patients, meaning it completely lost its effectiveness.
Another really tricky variable is hygroscopicity. Some drugs absorb moisture straight from the air, like calcium chloride. They absorb it so fiercely that they absolutely need special moisture-proof packaging. If you leave a highly hygroscopic drug out, it will literally pull water out of the air until it becomes a sticky mess, completely ruining its stability and flowability in the manufacturing machines.
We also have to carefully monitor the melting point, because if a drug melts at a low temperature, hot manufacturing methods are completely off the table. It's a great indicator of purity, sure, but practically speaking, if your drug turns into a puddle at 40 degrees Celsius, you definitely cannot use friction-heavy milling machines or high-heat drying processes.
Okay, so we've mastered the physical side, but this brings up a major puzzle piece. Why do drugs choose different absorption sites in the human body? Why does one pill work brilliantly in the highly acidic stomach, while another prefers the more neutral environment of the intestine to do its job?
We answer that in Section 4, Chemical Properties and Absorption. The answer lies purely in chemical properties, specifically ionization and the pKa of the drug. If you look at the diagram here, you can clearly see how weak acids, like aspirin, absorb really well in the highly acidic, low pH environment of the stomach. In that state, they remain unionized. Conversely, weak bases are designed for and absorb much better in the higher pH of the intestine.
Let's slow down for this next critical concept, the partition coefficient, or log P. Simply put, this measures how well a drug likes oil versus water. It's looking at its lipophilicity. A high log P means the drug distributes well into lipid or fat-based environments, which directly influences how easily it can permeate our lipid-heavy cell membranes.
For example, diazepam has a high log P. Because it is highly lipophilic, it easily punches right through the lipid-rich blood-brain barrier to cross into the brain and act powerfully as a CNS drug. If it didn't like oil as much, it would just bounce off that barrier and fail to deliver its therapeutic outcome.
And that brings us to our final section, Section 5, keeping drugs stable. Because honestly, understanding all these properties is totally useless if the drug degrades before the patient even takes it. Drugs can break down over time due to oxygen or light. Just look at this table. Hydrolysis destroys penicillin, oxidation attacks vitamin C, and photolysis breaks down drugs exposed to light. We also have to be super careful about drug-excipient compatibility. For instance, if you mix amine drugs with lactose, they can actually react and cause the drug to change color or break down. We call this the Maillard reaction, and formulators have to shield drugs from every single one of these threats.
By carefully studying these degradation pathways, particle sizes, and chemical structures, we can solve the puzzle. For example, during product selection, if a drug is unstable in a liquid form, we naturally prefer making it into a solid tablet instead. Every single property we've discussed guides the final product to ensure it's safe, stable, and works exactly as intended.
Let's quickly summarize. Physical pharmacy aims to make drug formulations safe and effective. Always check for polymorphism because it completely changes how a drug performs. Remember that hydroscopic drugs need protective packaging, and don't forget that amine drugs and lactose can react with each other. So I'll leave you with this to ponder. What unseen physicochemical property might be sabotaging the next breakthrough drug right in the lab today? Don't forget to subscribe for more simplified pharmacy tutorials.